Hi, this is a video on differentiating the natural exponential function, which is e to the x. I'm following James Stewart's calculus textbook, 6th edition. And in the video I did immediately preceding this, 7.3a asterisk, I defined the natural exponential function. Now we're going to talk about differentiating it. As it turns out, it is incredibly easy. I love this function. The derivative of the exponential function is the exponential function. It's a mirror of itself. What a miracle. It's wonderful. This makes this a very powerful kind of function. In fact, let me give you the interpretation. What does this mean to say that the derivative of e to the x is e to the x? Well, what it means is, it means that the slope of the tangent to this curve, y equals e to the x, the slope of the tangent to the curve e to the x is always the y coordinate of the point, because y equals, anyway. So this is fun. The y coordinate of each point of this function is also the slope of this function. Anyway, okay, so this is the basic claim of this video. Here's the proof. So we said in the immediately previous video that the natural logarithm and the natural exponential function are inverse functions. So if you switch the variables around, they cancel and all those sorts of things. So what this implies is, let me go ahead and take the derivative of the implicit. Let's do implicit differentiation of the natural log of y equals x. So if I take the derivative of the natural log of y, I know from, again, previous videos that this is going to be 1 over y times the derivative of y, okay, dy dx. And then if I take the derivative of this side, well, the derivative of x is 1. So I've got this little equation right here. Well, if I multiply both sides by y, then I have dy dx equals y. And I've already said up here that y equals e to the x. So, ta-da! I know that the derivative of the natural log of, well, anyway, I know that dy dx, if y equals e to the x, is going to be e to the x. So I have a proof of this. Easy to remember. The derivative of the natural exponential function is itself. Now, it can get a little bit more tricky if the exponent is not just an x, if it's something more complicated like x squared plus 1 or sine of x, or if e is raised to a function that is a little bit more complicated, then I have to use the chain rule. What's the chain rule? Well, here's the chain rule right here. That dy dx equals dy du times du dx, and the du's cancel. I'm left with dy dx. And so if I'm taking the derivative of e to something more complicated than x, yes, it is going to be e to the u, but then I have to take the derivative of the exponent as well. So the derivative of e to the u is the same as e to the u times the derivative of u. All right? Okay, so we're almost done with this video, believe it or not. Because these are just some basic things that if you don't remember the proofs, just memorize them. The derivative of e to the u is e to the u times the derivative of u with regard to x. And so if the derivative of e to the x is e to the x, then the integral of e to the x is also e to the x. That's the fundamental theorem of calculus. It goes back and forth. Plus a constant, of course, because if there was a constant here that was something other than 0, if you took the derivative of it, it would disappear. And so the integral of e to the x dx is e to the x plus a constant. That finishes this section of James Stewart's calculus textbook on differentiating the natural and integrating the natural exponential function.